On October 24, 2025, independent astronomers comparing live tracking data to official predictions noticed the impossible. Two spacecraft currently en route to entirely different destinations are on a collision course, not with a planet, not with an asteroid, but with the trailing ghost tail of a visitor from another star. They're about to fly right through the tail of the interstellar comet 3I Atlas. What they will find there could turn our understanding of the cosmos upside down and ask us what we're doing here, in a universe that reaches far beyond our home. If you're just as fascinated as we are by the incredible journey of 3I Atlas, hit that like button and subscribe so you never miss an update on the mysteries of space. Drop a comment below and let us know where you're listening from. Let's keep the cosmic conversation going. On July 1st, 2025, in the darkness before dawn, a telescope in Chile swept its gaze across a patch of southern sky. The Atlas Survey System, an automated sentinel designed to watch for asteroids that might threaten Earth, captured something in its field of view, a faint smudge of light, a moving point against the fixed stars. At first it seemed unremarkable. Space is full of rocks after all, chunks of debris left over from the formation of our solar system, wandering their eternal orbits around the Sun. But this one was different. Within hours, as more observations poured in from telescopes around the world, astronomers began to realize what they were looking at. The trajectory didn't fit. The mathematics didn't work. Every asteroid, every comet born in our solar system follows a predictable path. An ellipse, perhaps stretched long and thin, but always bound to the Sun's gravity, always returning. This object wasn't returning. Its path was hyperbolic, open-ended. It was moving too fast, coming from the wrong direction, tracing a curve through space that could only mean one thing. It came from somewhere else. Imagine that moment. Imagine being the astronomer who first ran those calculations, who first saw the numbers confirm what seemed impossible. This wasn't a piece of our cosmic neighborhood. This was a visitor from another star system entirely. The third such object ever confirmed in human history. They named it 3I Atlas, the I standing for interstellar, a designation that carries with it the weight of profound significance. When we say interstellar, we mean something that has travelled between the stars. Think about that for a moment. The distances between stars are so vast that we measure them in light years. The distance light itself, moving at 186,000 miles per second, travels in a year. That's nearly 6 trillion miles. And this object, this comet, had drifted through that darkness for who knows how long. Thousands of years, millions of years, perhaps longer. It's hard to comprehend what that means. We live our lives measured in hours and days, in the distances we can walk or drive. Our longest journeys span continents, perhaps from one side of Earth to the other. But 3I Atlas had crossed the gulf between stars. It had been travelling since before human civilization existed, before our species learned to farm or build cities, or look up at the night sky and wonder what those points of light might be. And now it was here, drifting through our solar system, close enough that we could see it with our telescopes, close enough that we could study it, learn from it, touch it, however briefly, with the instruments we've sent into space. The discovery electrified the astronomical community. Papers were rushed into preprint. Observing time on the world's most powerful telescopes was hastily scheduled. Every instrument that could be turned toward 3I Atlas was aimed at this unexpected guest. Because opportunities like this don't come along often. Before 3I Atlas, we had only seen 2 other confirmed interstellar objects. Oumuamua in 2017, that strange cigar-shaped visitor that tumbled through our inner solar system and vanished before we could study it properly. And Borisov in 2019, a comet that was easier to observe but still gone within months. These visitors arrive unannounced. They don't send advance notice. They don't slow down for us. They pass through our solar system like travellers on a cosmic highway, barely noticing the small blue world orbiting an average yellow star in the outer spiral arm of the galaxy. For them, we are just another stop on an infinite journey. But for us, each interstellar visitor is a revelation, a message in a bottle thrown across the vastness of space. Because these objects weren't formed here. They didn't condense from the same cloud of gas and dust that gave birth to our sun and planets 4.5 billion years ago. They were born around other stars in other stellar nurseries, shaped by different conditions, carrying with them the chemistry and history of alien solar systems we can barely imagine. When 3i Atlas entered our cosmic backyard, it brought with it questions we've been asking since humans first looked up at the stars and wondered if we were alone. Where did it come from? What is it made of? How old is it? What can it tell us about the universe beyond our own small corner of space? Some astronomers, looking at the early data, wondered if this might be another Oumuamua, an asteroidal object, dark and rocky, betraying no sign of the ices and volatiles we associate with comets. The trajectory suggested it. The initial brightness suggested it. But then, as the weeks passed and 3i Atlas drew closer to the Sun, something changed. Something awakened. This visitor wasn't done revealing its secrets. It was only just beginning to show us what it truly was. And what it was about to do would give us an opportunity that scientists had only dreamed about, a chance to reach out, across the interstellar void and touch, however gently, something born beneath an alien sun. What can it tell us? That question hung in the air as astronomers around the world turned their instruments toward this cosmic wanderer, watching, waiting, wondering what mysteries it might unlock. As the comet-designated 3i Atlas continued its plunge toward the inner solar system, astronomers worked feverishly to understand what they were dealing with. Every scrap of data mattered. Every observation added another piece to the puzzle, and slowly, orbit by carefully calculated orbit, the shape of this star traveller began to emerge. The trajectory itself was the first clue, the mathematical signature that marked 3i Atlas as foreign. Its path through space followed what astronomers call a hyperbolic orbit, not the closed ellipse of a solar system native, but an open curve, like one arm of a parabola stretched to infinity. The orbital eccentricity was measured at approximately 3.5, meaning this comet was moving far faster than the escape velocity of our solar system. It wasn't just passing through, it was destined to leave, to continue its journey through the galaxy, never to return to our Sun. The inclination of its orbit was equally striking. Picture the solar system as a flat disk, with the planets orbiting the Sun roughly in the same plane, what astronomers call the ecliptic. Now tilt that disk almost completely vertical. 3i Atlas was coming in at an angle of approximately 175 degrees relative to the ecliptic. It was diving almost straight down through our solar system, perpendicular to the orderly procession of planets. A ghost ship arriving unannounced into our backyard, approaching from an angle no solar system comet would naturally take. But what was it made of? How big was it? These basic questions proved frustratingly difficult to answer. The nucleus, the solid core of ice and rock at the heart of any comet, was small and distant, wrapped in the haze of gas and dust that would soon become its tail. Estimates varied wildly. Some measurements suggested a nucleus as small as 320 meters across, barely larger than 3 football fields placed end to end. Others suggested it could be as large as 5.6 kilometers, a genuine mountain of ice and rock tumbling through space. This uncertainty mattered because size tells us about history. A smaller nucleus means a younger comet, perhaps, or one that has made many passes close to other stars, boiled away over billions of years. A larger nucleus suggests something more primordial, better preserved, carrying with it a more pristine record of whatever stellar system gave it birth. In those early weeks, as 3i Atlas was still far from the Sun, there was genuine debate about what kind of object this actually was. Was it a comet, rich in ices that would sublimate and create the spectacular tales we associate with these wanderers? Or was it more like Oumuamua, that first interstellar visitor, which showed no signs of cometary activity, no tail, no coma of gas, just a dark, tumbling rock fleeing our solar system as mysteriously as it had arrived? The distinction mattered for more than just classification. Comets and asteroids tell different stories. Asteroids are rocky, metallic, the bones of failed planets, forged in heat. Comets are icy, dusty, the preservers of volatile compounds, frozen libraries of ancient chemistry. If 3i Atlas was an asteroid, it would tell us about the solid, rocky processes of planet formation in another stellar system. If it was a comet, it could tell us about the ices, the organic molecules, the chemical building blocks that might exist around other stars, the very ingredients from which life itself is made. For weeks, the debate continued. Telescopes tracked its motion, measured its brightness, analysed what little light they could gather from this distant speck. And then, as summer turned toward autumn, as 3C Atlas crossed inside the orbit of Mars and felt the sun's heat growing stronger with each passing day, the answer began to reveal itself. The ice began to wake. Water molecules, frozen for perhaps billions of years, began to sublimate. Carbon dioxide ice trapped in the comet's nucleus since its formation began to turn directly from solid to gas. And as these volatiles streamed away from the nucleus, pushed by the sun's radiation and the pressure of the solar wind, they carried with them dust, tiny particles of rock and organic compounds, creating around the nucleus a glowing envelope called the coma. 3I Atlas was a comet, a true comet, and it was about to put on a show. Astronomers watched with mounting excitement as the coma grew, expanding day by day. The comet brightened. Observations from telescopes around the world began to detect the characteristic signatures of water vapor, carbon monoxide, other molecular species streaming away from the nucleus. This wasn't just a rock from another star. This was ice, gas, dust, the primordial stuff of solar system formation, but formed around an alien sun, carrying with it the chemical fingerprint of another place, another time. And as it neared the sun, as the solar radiation grew stronger, and the solar wind pressed harder against the streaming gas and dust, something even more spectacular began to happen. The comet began to grow a tail, actually two tails, as all active comets do when they venture close to the sun. Its true nature had revealed itself. This visitor from another star was alive with activity, transformed by its passage through our solar system. And that transformation was about to give humanity an opportunity we never could have planned for, never could have predicted. The tail that was even now streaming millions of kilometers behind the comet's nucleus was about to intersect with something else in our solar system, something we had built, something we had sent into space with entirely different purposes in mind. To understand what was about to happen, you need to understand where 3I Atlas came from. Not just that it came from interstellar space, that much was obvious from its trajectory, but from where in the galaxy and when. Because recent analysis suggested something remarkable about this comet's origins, something that spoke to timescales so vast they challenged the imagination. In October 2025, researchers published a preprint paper analysing the likely birthplace of 3I Atlas based on its trajectory and velocity. What they found was humbling. This comet likely originated not from the thin disk of the galaxy, the spiral arms where most stars form today, where our sun itself was born 4.6 billion years ago, but from what astronomers call the thick disk. The thick disk is ancient. It's a population of older stars formed during an earlier epoch of our galaxy's history, roughly 9 to 13 billion years ago. That's only a few billion years after the Big Bang itself. When the stars that gave birth to 3I Atlas were forming, the universe was a younger, more turbulent place. The Milky Way galaxy was still taking shape. Our solar system wouldn't exist for another 4 to 8 billion years. Think about what that means. This object tumbling through our solar system right now may have been ejected from its parent star system billions of years before Earth existed, before our sun ignited, before the cloud of gas and dust that would become our solar system had even begun to collapse. While it was wandering the dark spaces between stars, the Milky Way continued to evolve. New stars were born and died, spiral arms formed and dissolved, and in one unremarkable corner of the galaxy, a molecular cloud began to collapse under its own gravity. That collapse would eventually form our sun, and the planets around it, and on one of those planets, life would emerge and evolve and eventually produce creatures capable of building telescopes and looking up at the night sky and spotting a faint smudge of light that had been travelling since before their world existed. The age of 3I Atlas, if the analysis is correct, means we're looking at a relic. A fossil not from our own solar system's history, but from the deep past of the galaxy itself. The ice locked in its nucleus might contain molecules formed in the disk of a star that died billions of years ago. The organic compounds in its dust could have been synthesized under conditions unlike anything in our own solar system. Every measurement we could make of this comet would be a window into an alien stellar system from an era we can barely conceive. Astronomers have long known that solar systems eject comets. It happens in our own system. When a comet passes too close to Jupiter or Saturn, the giant planet's gravity can fling it outward, accelerating it beyond the sun's escape velocity, sending it on a one-way trip into interstellar space. It's happening right now. Our solar system is probably sending thousands, maybe millions of comets into the galaxy every year. They drift outward, cooling, freezing solid, becoming inert chunks of ice and rock wandering the dark. And every star system is doing the same thing. Every solar system with giant planets is flinging comets into the void, which means the space between stars isn't empty. It's full of these wanderers, these exiles drifting through the darkness at a few kilometers per second, following ballistic trajectories that will carry them across the galaxy over millions and billions of years. Most of them never encounter another star. The distances are too vast. They just drift forever, frozen, dark, unobserved and unobservable. But occasionally, by pure chance, one of these wanderers passes close enough to another star to be captured by its gravity, or at least perturbed, sent on a new trajectory. And very occasionally one passes through a solar system in just the right way that the inhabitants of a small planet notice it, track it, study it. That's what was happening now with 3 Atlas. By sheer cosmic coincidence, this ancient wanderer from the thick disk had crossed paths with our solar system. The sun's gravity had bent its trajectory, pulling it inward, accelerating it as it fell toward the inner solar system, and the sun's heat was transforming it, waking the ancient ice, releasing gases that had been frozen since the age of the dinosaurs on Earth, or longer, perhaps since before multicellular life existed on our planet. The comet was being changed by its passage through our solar system. Ice that had been stable for billions of years was sublimating away. Dust that had been locked in place was streaming into space. The very structure of the nucleus was being altered, layers of material stripping away, craters forming as pockets of volatile ice burst through the surface. 3I Atlas would leave our solar system lighter than it arrived, its composition altered, its surface scarred. It was a one-time transformation. After 3I Atlas departed our solar system, it would drift back into the cold between stars, and the activity would cease. The ice would freeze solid again, the tail would dissipate, and the comet would return to being just another dark, silent wanderer, carrying with it the scars of its brief encounter with our sun. But before that happened, before it fled back into the dark, there was this moment, this brief window when the comet was active, transformed, blazing with reflected sunlight and streaming gas, when we could see it, study it, learn from it. And 2 spacecraft we had sent into space for entirely different reasons were about to fly through its tail. When you see a comet in the night sky, what you're seeing is mostly not the comet itself. The nucleus, the actual solid object, the mountain of ice and rock, is typically invisible to the naked eye, too small and dark to see from Earth. What you see is the coma and the tails. The coma is the glowing envelope of gas surrounding the nucleus, stretching hundreds of thousands of kilometers in every direction, and the tails are where the real spectacle happens. Every active comet develops 2 tails as it approaches the sun, though they're not always visible. The dust tail is the one most people picture when they think of comets, a broad, curved, yellowish streamer of tiny particles, each one reflecting sunlight like a microscopic mirror. These dust particles are blown away from the nucleus by the pressure of sunlight itself, photons striking the particles and pushing them outward. Because the comet is moving in its orbit, the dust tail curves, tracing a gentle arc behind the comet's path. But there's a second tail, often more impressive even if less visible to the naked eye. The ion tail is made not of dust but of charged gas molecules, ions, stripped from the comet's coma by ultraviolet light from the sun. These ions are caught by the solar wind, that constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second. The solar wind drags the ions along with it, creating a tail that points almost straight away from the sun regardless of the comet's motion. The ion tail is typically blue-white in colour, glowing with the fluorescence of carbon monoxide ions, water ions, and other molecular fragments. The ion tail can stretch for tens of millions of kilometres, sometimes even farther. It's an incredibly tenuous structure, far more rarefied than the best vacuum we can create in laboratories on Earth. If you could somehow stand in the ion tail of a comet, you probably wouldn't notice it. The density of particles is so low that they barely interact. You'd be an essentially perfect vacuum, with just the occasional molecule drifting past. But from a distance, seen against the darkness of space, the ion tail is spectacular. It's a cosmic windsock showing the direction and strength of the solar wind, rippling and twisting as disturbances in the solar wind pass through it. Time-lapse images of comets often show the ion tail waving, disconnecting and reforming, responding in real time to the changing conditions in the space environment around the Sun. For 3I Atlas, the tail began to develop in August and September 2025 as the comet crossed inside Mars's orbit. Early images from amateur astronomers showed a faint, elongated glow. By September, professional observatories were capturing detailed images showing the tail structure. The coma itself had grown to approximately 100,000 kilometers across, larger than Jupiter, though far less massive, and stretching behind it was the characteristic blue-white ion tail, already millions of kilometers long and growing longer with each passing day. There was another feature too, something that had briefly puzzled observers earlier in the summer: an apparent spike of light pointing toward the Sun, what's called an anti-tail. This wasn't a tail pointing the wrong direction, defying the physics of solar radiation. It was an optical illusion, a projection effect. When we see a comet from Earth, we're seeing it from a specific angle. Sometimes that angle is such that the dust tail, which curves and spreads out in 3 dimensions, appears to point back toward the Sun. It's like looking at a curved object from the side and seeing only the edge. As 3I Atlas moved in its orbit and our viewing geometry changed, the anti-tail vanished, replaced by the more typical tail structure streaming away from the Sun. By early October, the comet was inside Earth's orbit, approaching its closest point to the Sun, perihelion, which would occur on November 1st. The tail was now at its most active, streaming millions upon millions of kilometers behind the nucleus. Molecules were being stripped from the coma at a tremendous rate. The solar wind was blowing at full force, carrying the ions away. And that tail, that incredibly long, incredibly tenuous structure of charged particles and magnetic fields, was about to be traversed by something humans had built. Actually, not by one spacecraft, by 2. This is where the story becomes almost unbelievable, because we didn't plan this. We didn't launch missions to intercept 3I Atlas. We didn't have time. The comet was only discovered in July, and spacecraft take years to build and launch. But by an extraordinary coincidence, 2 spacecraft already in flight, launched years ago for entirely different missions, were going to pass through 3I Atlas's ion tail within days of each other. The first spacecraft was Hera, a European Space Agency mission launched in October 2024, a full year before 3I Atlas was even discovered. Hera's mission was to study the aftermath of a planetary defense test, examining the asteroid Dimorphos after it had been deliberately struck by an earlier spacecraft. Hera was on its way to the asteroid belt, following a carefully calculated trajectory that would take it past Mars and eventually to its target. The second spacecraft was Europa Clipper, a NASA mission launched in October 2024 as well, designed to study Jupiter's ice-covered moon Europa. Clipper was on a complex trajectory that would take it past Mars for a gravity assist, using the red planet's gravity to help fling it toward the outer solar system. 2 spacecraft, 2 completely different missions, 2 destinations light years apart in terms of their scientific goals, and both, by pure cosmic chance, were going to fly through the ion tail of an interstellar comet. The discovery of this alignment came from a preprint paper published on October 15, 2025 by researchers Grant and Jones. They had been tracking 3I Atlas's trajectory, modelling the extent of its ion tail based on solar wind conditions and the comet's gas production rate, and comparing that to the known trajectories of spacecraft in the inner solar system. When they ran the numbers, they found the overlap. Hera and Europa Clipper would both pass through regions of space where 3I Atlas's ion tail would be, not close to the nucleus. The spacecraft wouldn't see the coma or the nucleus itself. They were too far away for that. But the ion tail, that vast gossamer structure stretching millions of kilometers, would envelop them. The spacecraft would fly through it, their instruments recording data the whole time, capturing measurements of particles and magnetic fields that originated from an object born in another star system. This was unprecedented. Never before had we been able to study an interstellar object in situ, with instruments actually travelling through its immediate environment. Oumuamua had been observed only from Earth, and even that only after it was already leaving. Borisov had been studied extensively with telescopes, but never visited by spacecraft. But now, without planning it, without even knowing 3I Atlas existed until a few months ago, we had 2 spacecraft positioned to fly through its tail. It was the kind of opportunity scientists dream about, a chance to touch an object from another star system without launching anything new, without spending billions of dollars on a dedicated mission, without waiting years for a spacecraft to reach its target. Hera and Europa Clipper were already there, already on their trajectories, already collecting data. And in late October and early November, they would add to their mission objectives something nobody had planned for: the first in situ sampling of material from an interstellar comet. What would they find? What could their instruments tell us about this visitor from the thick disk, this relic of ancient star formation? The ion tail would contain molecules stripped from the comet's nucleus, ionized by solar radiation, accelerated by the solar wind. Analysis of those ions could reveal the chemical composition of 3I Atlas, the isotopic ratios that would constrain where and when it formed, the presence of organic compounds that might speak to the chemistry of its birth system. Every molecule would be a clue, every measurement would be a piece of the puzzle, and we were about to get data that would have been impossible to obtain any other way, delivered to us by spacecraft that happened to be in the right place at exactly the right time. When they crossed that tail, what would they find? Could it change everything? Could the chemistry be different from what we expect, suggesting formation conditions unlike anything in our own solar system? Could there be isotopic anomalies pointing to processes we don't understand? Could there be organic molecules we've never seen before, hinting at the incredible diversity of chemistry possible around other stars? The answers were waiting, suspended in that tenuous tail of ions streaming millions of kilometers behind a mountain of ancient ice, and in just days, we would have them. It's in October 2024, a year before anyone knew that 3I Atlas existed. The European Space Agency launched a spacecraft called Hera from Cape Canaveral in Florida. It lifted off on October 7th aboard a SpaceX Falcon 9 rocket, carrying with it a mission that represented humanity's first steps toward actively defending our planet from cosmic threats. Hera wasn't designed to destroy asteroids or deflect them in some dramatic Hollywood fashion. Its purpose was quieter, more methodical, but no less important: to study the aftermath of the first deliberate attempt to change an asteroid's orbit. 2 years before Hera's launch, in September 2022, NASA had sent a spacecraft called DART, the Double Asteroid Redirection Test, on a one-way mission to crash into a small asteroid moon called Dimorphos. Dimorphos orbited a larger asteroid named Didymos, and together they formed a binary system, 2 rocky bodies locked in their own private dance as they orbited the Sun. DART struck Dimorphos at over 22,000 kilometers per hour, and the impact changed the smaller asteroid's orbit around its companion. It was proof of concept. Humanity could, if necessary, nudge an asteroid off a collision course with Earth. But that was just the first step. What happened after the impact? How much material was ejected? What did the crater look like? How did the asteroid's internal structure respond to the collision? These were the questions Hera was designed to answer. It would travel to the Didymos system, arrive in late 2026, and spend months studying Dimorphos up close with cameras, spectrometers, radar, and 2 small CubeSats it would deploy to examine the asteroid from multiple angles simultaneously. Hera's trajectory was carefully planned. After launch, it followed a path that would take it past Mars in March 2025 for a gravity assist, using the red planet's gravity to adjust its course and speed, flinging it onward toward the asteroid belt. From there, it would continue to Didymos, arriving nearly 2 years after launch. Every kilometer of that journey was calculated, every maneuver planned, every instrument check scheduled. The mission timeline was precise, the objectives clear. And then, in July 2025, as Hera was already millions of kilometers from Earth, coasting through the inner solar system on its way to Mars, astronomers in Chile discovered 3I Atlas. At first, the discovery seemed irrelevant to Hera's mission. An interstellar comet was certainly exciting, certainly worthy of study, but Hera was committed. It couldn't change course. Its trajectory was locked in, its destination fixed. The spacecraft was going to Didymos, and nothing could alter that. Or so it seemed. But then, in early October, researchers began to model the tail of 3I Atlas. As the comet approached the Sun and its activity increased, its ion tail grew longer and longer, stretching millions of kilometers behind the nucleus. The tail wasn't a solid structure, it was more like a cone, widening as it extended, sweeping out a vast volume of space as the comet moved in its orbit. And when Grant and Jones ran their calculations, comparing the predicted extent of the tail with the known trajectories of spacecraft in the inner solar system, they found something remarkable. Hera was going to fly through it. Not close to the comet itself, Hera would be approximately 8.2 million kilometers from the tail's central axis, the imaginary line running from the Sun through the comet's nucleus and extending behind it. At that distance, Hera wouldn't see the nucleus, wouldn't detect the coma, wouldn't be in any danger from dust particles. But the ion tail of an active comet can extend far beyond the central axis, spreading out in a diffuse cone that can be millions of kilometers wide. The encounter window was predicted to be between October 25th and November 1st, 2025. During that week, Hera would be flying through a region of space that contained ions stripped from the nucleus of 3I Atlas, atoms and molecules that had been frozen in the comet's ice for billions of years, sublimated as the comet approached the Sun, ionized by solar ultraviolet radiation and swept away by the solar wind. Think about what this meant. A spacecraft built to study the aftermath of a planetary defense test, launched a year before the comet was even discovered, would now become part of humanity's first in situ study of an interstellar object. Without replanning the mission, without changing course, without spending a single extra dollar, Hera would collect data that planetary scientists and astrochemists could only dream of. The European Space Agency began to prepare. Hera's instruments weren't designed specifically to study cometary ions, but many of them could still collect useful data. The spacecraft's radiation monitors would detect any changes in the charged particle environment. Its magnetometers would sense disturbances in the magnetic field caused by the interaction between the solar wind and the cometary ions. Even its communication systems might register fluctuations as the spacecraft passed through regions of ionized gas. It was a gift, an unexpected, unplanned, almost unbelievable gift from the universe. A mission designed to protect Earth from asteroid impacts would now help us understand the composition of objects from other star systems. The poetry of it was hard to miss. Humanity reaching outward to ensure our survival, and in doing so stumbling into knowledge about the cosmos that we could never have anticipated. But there was something even more extraordinary about this cosmic coincidence. Because Hera wasn't alone in this story. There was another spacecraft launched the same month as Hera, following a completely different trajectory to a completely different destination, that would also pass through the tail of 3I Atlas, and that spacecraft was searching for life. On October 14th, 2024, exactly 1 week after Hera's launch, NASA sent Europa Clipper into space atop a SpaceX Falcon Heavy rocket. It was one of the most ambitious planetary science missions ever conceived, designed to answer one of the most profound questions in all of science. Does life exist elsewhere in our solar system? The target was Europa, one of Jupiter's 4 large moons, discovered by Galileo in 1610 when he first turned a telescope toward the giant planet. For centuries, Europa was just a point of light in Jupiter's orbit, one moon among many. But in the 1990s, when the Galileo spacecraft arrived at Jupiter and began a multi-year tour of the system, it discovered something extraordinary about Europa. Beneath its icy crust lay an ocean. Not a lake, not a sea, an ocean. A global ocean of liquid water, perhaps 100 kilometers deep, containing more water than all of Earth's oceans combined. The ice shell that covers Europa is estimated to be 15 to 25 kilometers thick. But beneath that frozen barrier is a world of liquid water that has existed for billions of years, kept warm by tidal heating. The gravitational flexing caused by Europa's elliptical orbit around Jupiter. Where there is liquid water, there could be life. At least that's the hypothesis. On Earth, life exists everywhere liquid water exists, in boiling hot springs, in Antarctic ice, in the deepest ocean trenches, in underground aquifers kilometers below the surface. Life, it seems, needs water, and Europa has water in abundance. Europa Clipper wasn't designed to land on Europa or drill through the ice. That would be a mission for a future generation. Instead, Clipper would orbit Jupiter and make repeated close flybys of Europa, 49 in total, getting as close as 25 kilometers above the Moon's surface. Its instruments would map the ice shell in unprecedented detail, measure its thickness, search for thin spots where the ice might be more easily penetrated. It would analyze the composition of Europa's surface, looking for organic molecules, salts, and other chemicals that might have bubbled up from the ocean below. It would even search for plumes, geysers of water vapor erupting from cracks in the ice, and if it found them, it would fly through them, directly sampling material from Europa's subsurface ocean. The journey to Jupiter was long. Europa Clipper couldn't fly directly there. It needed gravity assist to build up enough speed to reach the outer solar system. The trajectory planners designed a route that would take the spacecraft past Mars in March 2025 for a gravitational boost, then back past Earth in December 2026 for another assist, and finally out to Jupiter, arriving in April 2030. It was a carefully choreographed cosmic ballet, using the gravity of planets to fling the spacecraft faster and faster, conserving fuel, making the journey possible. Every maneuver was calculated years in advance. Every parameter was locked in. Europa Clipper was committed to its path, following a trajectory that would carry it through the inner solar system on its way to the frozen moon orbiting the giant planet. And then 3I Atlas arrived. When Grant and Jones calculated the extent of the comet's ion tail and compared it to the trajectories of spacecraft in the solar system, they found that Europa Clipper would also intersect the tail. The predicted encounter window was October 30th to November 6th, 2025, with the spacecraft passing approximately 8 million kilometers from the tail's central axis, nearly the same distance as Hera, but at a slightly different time and from a different angle. 2 spacecraft, 2 missions launched within a week of each other in October 2024. One headed to an asteroid to study planetary defense, one headed to an icy moon to search for the conditions for life, and both, by pure chance, positioned to fly through the ion tail of an interstellar comet that wouldn't even be discovered until 9 months after they launched. The odds of this happening were astronomical. There are dozens of spacecraft operating in the solar system at any given time, but most are in Earth orbit or on the surface of other planets. Only a handful are travelling through interplanetary space on trajectories that might intersect with a comet's tail. And for 2 of them to be positioned correctly at the same time, for the same comet, an interstellar comet no less, only the 3rd ever detected, defied probability. But it was happening. The universe, in its infinite complexity, had aligned circumstances in just the right way. A comet ejected from a star system billions of years ago had wandered across light years of space, entering our solar system at just the right angle and speed. 2 spacecraft had been launched in 2024 on trajectories calculated years before, and in late October 2025 those trajectories would intersect with the comet's tail within a window of just a few weeks. NASA began preparing Europa Clipper's instruments. Like Hera, Clipper wasn't specifically designed to study cometary tails, but it carried a suite of instruments that could collect valuable data. Its magnetometer would detect magnetic field disturbances. Its plasma instrument, designed to study the charged particle environment around Jupiter, would be able to detect ions from the comet. Its mass spectrometer could potentially identify specific molecules if the ion density was high enough. 2 missions, 2 objectives, 1 unexpected alignment. A mission looking for life beneath the ice of an alien moon would now help us study material from another star system. A mission designed to protect Earth from asteroids would contribute to our understanding of interstellar chemistry. Neither spacecraft was designed for this. Neither mission team had planned for it. But the cosmos had other ideas, and as October turned toward November, as both spacecraft hurtled through space on their separate journeys, the tail of 3I Atlas swept across their paths like a cosmic curtain waiting to be drawn back. Picture it. Imagine the scene unfolding in the cold silence of space, millions of kilometers from Earth, far from the warmth of the sun. Hera is a small spacecraft roughly the size of a car. Its solar panels spread like wings to catch the faint sunlight. It's travelling at tens of thousands of kilometers per hour, a speed incomprehensible to human experience, yet barely moving by cosmic standards. The spacecraft is automated, intelligent, following commands uploaded weeks or months ago, executing its mission timeline with mechanical precision. Inside its metal chassis, instruments hum with electricity. Sensors monitor temperature, radiation, magnetic fields. Antennas maintain a tenuous link with Earth, sending back data at the speed of light, data that still takes minutes to arrive, even travelling at 300,000 kilometers per second. The spacecraft doesn't know it's about to fly through the tail of an interstellar comet. It has no awareness, no understanding of the cosmic significance of what's happening. It's just following its programmed trajectory, collecting data as it always does, every second of every day. But the space around it is changing. The solar wind, that constant stream of charged particles flowing outward from the sun, is always present in interplanetary space. It's mostly protons and electrons, with traces of heavier ions, all moving at hundreds of kilometers per second. Hera's instruments have been measuring this solar wind since launch. They know what normal looks like. They know the typical density, the typical velocity, the typical composition. But as Hera crosses into the region where 3I Atlas's ion tail extends, things begin to change. New ions appear in the data stream, not just protons and electrons from the sun, but heavier ions, water ions, carbon monoxide ions, carbon dioxide ions, perhaps even more complex molecules. These are pickup ions, atoms and molecules that were neutral when they left the comet's nucleus, but have since been ionized by solar ultraviolet radiation and picked up by the solar wind, accelerated and carried along with it. The magnetic field starts to behave strangely. The solar wind carries with it the sun's magnetic field, dragged along by the flowing plasma. But when the solar wind encounters the ions from the comet, the magnetic field drapes around them, distorts, creates a bow wave like water flowing around a rock in a stream. Hera's magnetometers detect these distortions, subtle but measurable. The radiation environment shifts. Cosmic rays, high-energy particles from outside our solar system, are normally deflected by the solar wind's magnetic field. But in regions where the magnetic field is disturbed, where pickup ions are abundant, the cosmic ray flux can change. Hera's radiation monitors note the variation. All of this is being recorded, time-stamped, stored in the spacecraft's memory for later transmission to Earth. Terabytes of data, most of it unremarkable, but buried within it are the signatures of something extraordinary. The presence of material from an object born around another star, and Europa Clipper, days later, will fly through the same region and record similar data. Its instruments will see the same signatures, perhaps from a different angle, perhaps with different sensitivity. 2 spacecraft, 2 sets of measurements, 2 independent confirmations of what's there. This is what an ion tail encounter looks like, not a dramatic collision, not a visible event that human eyes could appreciate. Just subtle changes in measurements, fluctuations in data streams, anomalies that scientists will later analyze and debate and attempt to understand. The tail itself is invisible. If you could somehow stand in space and watch the spacecraft fly by, you would see nothing unusual, no glow, no color, no indication that anything special was happening. But it is happening. These 2 machines, these products of human ingenuity and ambition, are brushing against the ghostly remnants of an ancient traveller. Like a ghostly ribbon of charged particles streaming behind the comet, invisible yet real, touching these machines built by a civilization that didn't exist when the comet was ejected from its birth system. There's a profound humanity to this moment. We built Hera to understand how to protect our planet from asteroid impacts, a mission born from the recognition that Earth is vulnerable, that cosmic collisions have shaped our planet's history and will shape its future, and that we have a responsibility to defend our world if we can. We built Europa Clipper to search for life, to explore an ocean world, to answer the ancient question of whether we are alone in the universe. These are fundamentally human endeavours. They arise from our curiosity, our fear, our hope, our desire to understand and survive and discover. We pour billions of dollars into these missions, decades of planning, the careers of thousands of engineers and scientists. We launch them into space with specific objectives, clear goals, defined timelines, and then the universe surprises us. An interstellar comet appears, unannounced, following a trajectory we couldn't have predicted. And by sheer cosmic coincidence, 2 of our spacecraft are in exactly the right place, at exactly the right time to study it. We didn't plan for this. We couldn't have planned for it. But here it is, happening, a gift from the cosmos that reminds us how little we control and how much we have yet to discover. This is one of the greatest cosmic coincidences in the history of space exploration. Not since Voyager 2's grand tour of the Outers, Planets has a mission been able to accomplish something so far beyond its original design. And unlike Voyager, which was at least designed with the possibility of visiting multiple planets, Hera and Europa Clipper weren't designed to study comets at all, let alone interstellar ones. But what exactly might they measure? And why does that matter so much? When scientists talk about studying the tail of Three-Eye Atlas, they're talking about extracting information from incredibly subtle signals. The ion tail isn't dense. Even near the nucleus, the density of particles is lower than the best laboratory vacuum we can create on Earth. By the time you get 8 million kilometers from the central axis, where Hera and Europa Clipper will cross, the density is even lower. There might be only a few additional ions per cubic centimeter compared to the background solar wind. But those few ions matter, because they carry information. Every atom and molecule in the comet's tail originated in the comet's nucleus. They were once part of the ice and rock that makes up the solid body of Three-Eye Atlas. When the comet approached the Sun, heat caused those ices to sublimate, turning directly from solid to gas without passing through a liquid phase. Water ice became water vapor. Carbon dioxide ice became carbon dioxide gas. Frozen carbon monoxide, ammonia, methane, and more complex organic molecules all vaporized and streamed away from the nucleus. Once in the coma surrounding the nucleus, these molecules were exposed to intense ultraviolet radiation from the Sun. That radiation stripped electrons from the molecules, ionizing them, turning them into charged particles, and once charged they could be picked up by the solar wind's magnetic field and carried away, joining the flow of particles streaming from the Sun, creating the ion tail. What Hera and Europa Clipper can potentially measure are the signatures of these pickup ions. Their instruments can detect the presence of ions with different mass-to-charge ratios, identifying what molecules are present. Water ions, carbon monoxide ions, carbon dioxide, nitrogen compounds, sulfur compounds, complex organic molecules. The composition matters because it tells us what the comet is made of, and that, in turn, tells us about the conditions in the protoplanetary disk where it formed. The disk of gas and dust surrounding another star billions of years ago that eventually coalesced into planets, moons, asteroids, and comets. Different stellar systems have different compositions. The ratio of carbon to oxygen, the abundance of nitrogen, the presence of specific isotopes, all of these vary depending on when and where the star formed, what generation of stellar evolution it belongs to, what supernovae contributed material to the molecular cloud that gave it birth. A comet from the thick disk of the galaxy, formed 9 to 13 billion years ago, might have a very different composition from comets in our own solar system, which formed only 4.6 billion years ago. By analysing the ions in Three-Eye Atlas's tail, scientists can begin to reconstruct the chemistry of its birth environment. They can compare isotopic ratios, the relative abundance of different isotopes of the same element, with what we see in our own solar system. They can look for unusual molecules, compounds that are rare or absent in our comets, but common in this interstellar visitor. Beyond composition, the spacecraft can measure how the solar wind interacts with the cometary ions. This is the study of plasma physics in action. When the fast-moving solar wind encounters the slower-moving pickup ions from the comet, interesting things happen. The ions disturb the magnetic field carried by the solar wind, creating waves, instabilities, turbulence. The solar wind can accelerate the pickup ions, giving them energy. The pickup ions can, in turn, extract energy from the solar wind, slowing it down. All of these interactions leave signatures in the data. The magnetometers on Hera and Europa Clipper can measure the distortions in the magnetic field. The plasma instruments can measure the velocity distributions of ions, seeing how the pickup process changes their motion. The radiation monitors can detect energetic particles created by the acceleration processes. This might sound esoteric, but it's actually fundamental to understanding how comets work. Every comet that approaches the Sun goes through these processes. sublimation, ionization, pick up by the solar wind. We've studied this with solar system comets, but never with an interstellar one. If the composition is different, if the isotopic ratios are different, then the interaction with the solar wind might be different too. The tail structure could be different. The magnetic field draping could be different. There might be surprises, and that's what makes this so exciting, because we don't know what we're going to find. The data could confirm that 3I Atlas is similar to our own comets, suggesting that comet formation is a universal process that doesn't vary much from star to star. Or the data could reveal something completely unexpected: unusual molecules, strange isotopic ratios, magnetic field behavior that doesn't match our models, forcing us to rethink our understanding of how comets form and evolve. There's another detail worth mentioning. The dust tail of 3I Atlas will not be sampled by either spacecraft. The dust tail, made of solid particles rather than ions, follows a different trajectory. Because dust particles are pushed by the pressure of sunlight and not carried by the solar wind, they trail behind the comet in a curved arc that depends on the size and mass of the particles. Grant and Jones's calculations showed that the dust tail doesn't intersect with the trajectories of Hera or Europa Clipper during the encounter window. This means the encounters will be pure ion tail measurements. No dust grains striking the spacecraft, no risk of contamination or damage from particles. Just the subtle, almost ethereal presence of ionized molecules in the vacuum of space. In a way, this is even more elegant. The ion tail is pure information, molecules from the comet, transformed by the sun's radiation, carried by the solar wind, waiting to be detected and analyzed. It's like reading a postcard from another world, written in the language of atomic and molecular physics, delivered across billions of years and trillions of kilometers by processes we're only beginning to understand. This is why the encounter matters. This is why scientists are so excited. Not because anything dramatic will happen, but because something subtle and profound will occur. 2 spacecraft will pass through a region of space that contains atoms and molecules from an object formed in another stellar system, and they will record what they find. And from that data we will learn something about the universe beyond our own small corner of it. But there are risks and unknowns, and the very real possibility that the encounter will yield less data than hoped. Space missions are exercises in managing uncertainty. Engineers and scientists plan for years, modeling every conceivable scenario, testing equipment, running simulations. But you can never eliminate all the unknowns. And with the 3I Atlas tail encounters, the unknowns are substantial. Start with the most basic question. How dense is the ion tail at 8 million kilometers from the central axis? The models say there should be detectable ions there. The calculations suggest that the tail is wide enough to extend that far. But models are only as good as their assumptions, and there are a lot of assumptions baked into the tail modeling. How much gas is the nucleus producing? That depends on its size, its composition, its temperature, how much of its surface is actively sublimating. All of these are estimated from Earth-based observations, but there's uncertainty in every parameter. If the gas production rate is lower than expected, the tail will be less dense, extending less far from the central axis. How fast is the solar wind moving? How strong is the sun's magnetic field? These vary over time, sometimes dramatically depending on solar activity. A burst of fast solar wind can sweep the tail away more efficiently, creating a denser but narrower structure. A slow solar wind lets the ions spread out more, creating a wider but more diffuse tail. What's the geometry? The ion tail points roughly away from the sun, but it's not a perfect straight line. The solar wind's magnetic field is wrapped into a spiral pattern by the sun's rotation, the Parker spiral. Ions picked up by the solar wind follow that spiral, creating a tail that curves slightly. The exact shape depends on the solar wind speed and the comet's velocity. If the geometry is slightly different from the models, the spacecraft might miss the densest regions of the tail entirely. And then there are the instruments themselves. Hera and Europa Clipper carry sophisticated equipment, but they weren't optimized for this kind of measurement. Their plasma instruments are designed to measure the solar wind, not cometary pickup ions. They have sensitivity limits, dynamic ranges, sampling rates that were chosen for their primary missions, not for a chance encounter with an interstellar comet. If the ion density is at the low end of predictions, the instruments might barely detect anything above background noise. The signal could be so subtle that it takes months of careful analysis to tease it out from the data, or it might not be detectable at all. There's also the question of duration. Each spacecraft will be in the predicted tail region for several days, but several days is not very long compared to the time it takes to accumulate statistics in low-density environments. Every ion detection is a random event, following Poisson's statistics. You need to detect enough ions to be confident that what you're seeing is real, and not just statistical fluctuation. If the tail is thinner than expected, if the encounter is briefer than predicted, there might not be enough data to draw firm conclusions. Mission controllers and scientists are acutely aware of these uncertainties. They've spent weeks preparing for the encounters, planning special observation sequences, maximizing the chances of detecting something useful. But they also know that they might come up empty-handed. Space exploration is full of disappointments, of missions that don't find what they're looking for, of instruments that fail at critical moments, of opportunities that slip away because the universe didn't cooperate. The human side of this can't be ignored. Behind every space mission are people, engineers who designed the spacecraft, scientists who planned the observations, mission controllers who operate the systems, data analysts who will sift through the telemetry. Many of them have devoted years or even decades of their careers to these missions. They've worked long hours, solved countless problems, overcome setbacks and budget cuts and technical challenges, and now, suddenly, their spacecraft are part of something they never anticipated. Something historic. The first in situ measurements of an interstellar object's environment. It's exciting, but it's also stressful. Because they know the stakes. They know that this opportunity won't come again, at least not with these spacecraft. If they don't capture the data properly, if they miss something critical, if the instruments aren't configured correctly, they'll have lost a once-in-a-lifetime chance. The encounters are fleeting. Hera will be in the tail region for about a week. Europa Clipper for perhaps a few days longer. During that time, the spacecraft will continue their primary mission operations. They can't stop everything else just to focus on the comet tail. They have to balance competing priorities, maintaining spacecraft health, staying on trajectory, communicating with Earth, collecting data for their primary science objectives. But within those constraints, they'll do everything possible to capture whatever signals the tail might provide. Extra data downloads will be scheduled, ground stations will track the spacecraft more frequently. Scientists will be on call, ready to analyze data as it arrives, looking for the telltale signatures of cometary ions. It's high-stakes science. The outcome is uncertain. The data might be ambiguous. The results might not be conclusive. But that's the nature of exploration. You don't know what you'll find until you look. And sometimes, the universe surprises you. At this moment, as you are listening to this, those spacecraft might already be crossing the stream of an alien traveller's wake. Hera may already be recording fluctuations in its magnetometer readings, detecting ions with unfamiliar mass signatures, noting changes in the plasma environment that signal the presence of material from beyond our solar system. Europa Clipper may be just days away from its own encounter, instruments primed, data recorders spinning, antennas pointed toward Earth to relay whatever secrets the comet's tail might reveal. Right now, somewhere in the cold vacuum of space millions of kilometers from Earth, atoms and molecules that were frozen into ice billions of years ago, that travelled across light years of interstellar darkness, that witnessed the youth of our galaxy when our own solar system was not yet born. Those atoms are streaming past human-made machines, leaving their signatures in digital memory, becoming part of humanity's growing understanding of the cosmos. The data is being collected, the measurements are being made, and soon, very soon, we will begin to understand what 3i Atlas has to tell us. Stop for a moment and think about what it means to study something like 3i Atlas. This isn't just about observing a comet. We observe comets all the time. Every year, dozens of comets become visible from Earth, some bright enough to see with the naked eye, others requiring telescopes. We've sent spacecraft to comets before, missions that have orbited them, landed on them, even collected samples and brought them back to Earth. We know comets. We understand their basic structure, their composition, how they behave as they approach the Sun. But 3i Atlas is different. It's not just another comet. It's a messenger from another stellar system, carrying information about conditions and processes that occurred not here, not in our solar system, but somewhere else entirely. somewhere we can never visit, somewhere so distant that light from that region of the galaxy takes thousands or tens of thousands of years to reach us. When scientists analyze the composition of 3I Atlas, they're not just learning about one object, they're learning about the star system that gave it birth. The isotopic ratios in the comet's ice reflect the composition of the molecular cloud from which its parent star formed. The organic molecules in its dust reveal what chemical processes occurred in that protoplanetary disk. The ratio of different elements, carbon to oxygen, nitrogen to hydrogen, tells us about nucleosynthesis, about what generations of stars contributed material to that particular region of the galaxy. This is cosmochemistry written in frozen water and ancient dust. Every measurement we can make is a glimpse into an alien world that existed billions of years ago. And here's where the story gets even more profound. Recent analysis suggests that 3I Atlas likely originated from a star system formed during what astronomers call cosmic noon. Not literally noon, but a period in the history of the universe when star formation was at its peak, when galaxies were churning out new stars at rates far higher than what we see today. This epoch occurred roughly 9 to 13 billion years ago, when the universe was between 1 and 5 billion years old. Think about that timeline. The Big Bang occurred 13.8 billion years ago. For the first few 100 million years, the universe was dark. No stars, just expanding gas cooling and clumping under its own gravity. Then the first stars ignited, massive and short-lived, exploding as supernovae and seeding the cosmos with heavier elements. Those elements allowed the formation of later generations of stars, and with them came planets, asteroids, and comets. By the time cosmic noon arrived, the universe was a busy place. Star formation was happening everywhere. The Milky Way's thick disk, that population of older stars distributed above and below the main galactic plane, was being populated. And in one of those stellar systems, perhaps 8 or 10 or 12 billion years ago, a comet formed. Maybe it was one of thousands or millions of comets in that system, part of a vast cloud of icy bodies orbiting far from the parent star, analogous to our own Oort cloud. Something happened. Perhaps a passing star disturbed the comet's orbit. Perhaps a giant planet in that system gravitationally ejected it. Whatever the mechanism, the comet was flung outward, accelerated beyond escape velocity, sent on a trajectory that would carry it away from its birth star forever. And it drifted, for billions of years, through the spiral arms of the Milky Way, through regions of dense molecular clouds and regions of near-perfect vacuum. Past other stars, perhaps, but never close enough to be captured, just drifting, frozen, inert, a tiny speck of ice and rock among trillions of others, invisible and undetectable, until now, until it happened to pass close enough to our sun to be pulled inward, heated, transformed, observed. The journey that brought it here began when the universe was young, when our own galaxy was still forming its structure, when the solar system that would eventually produce humanity didn't yet exist. We are connected to that deep time. The atoms in our bodies were forged in stars that exploded billions of years ago. The water we drink, the air we breathe, the calcium in our bones, all of it cycled through stellar furnaces and supernova explosions before eventually becoming part of the molecular cloud that formed our sun and planets. We are quite literally made of stardust, and so is 3I Atlas, but it's stardust from a different place, a different time, a different stellar system. When Hera and Europa Clipper fly through the tail of 3I Atlas, when they detect ions that originated in that ancient comet's nucleus, they're sampling material from another world, not another planet, something more fundamental. Another stellar system, another branch of cosmic evolution, another outcome of the same physical laws that govern our own corner of the universe, but played out under different initial conditions, with different abundances of elements, perhaps with different outcomes. This is why studying interstellar objects matters. They connect us to the broader galaxy. They remind us that our solar system is not isolated, not unique, not the only place where these processes occur. Comets form around other stars. Planets form around other stars, and if planets form, if organic chemistry occurs, if liquid water exists, then perhaps life arises, evolves. looks up at its own sky and wonders about other worlds. We don't know if the star system that ejected 3I Atlas still exists. Stars in the thick disk are old. Some have already died, either fading away as white dwarfs or exploding as supernovae. The planets that once orbited that star, if there were any, are gone or unrecognizable, reshaped by billions of years of cosmic evolution. But this comet survived. This frozen remnant endured. And now it's here, passing through our solar system, giving us a chance to study it. And yet, this visitor is fleeting. Comets don't linger. 3I Atlas reached perihelion, its closest approach to the Sun, on November 1st, 2025. After that, it will begin its outward journey, accelerating as the Sun's gravity flings it back toward interstellar space. Within months, it will be too faint to observe from Earth. Within a year or two, it will cross beyond the orbit of Neptune, heading back into the darkness beyond our planetary system. It will never return. Its hyperbolic trajectory means it's a one-time visitor. This is our only chance to study it. The window for observation is measured in weeks or months at most. After that, 3I Atlas will rejoin the vast population of interstellar wanderers drifting through the galaxy, forever beyond our reach. We have to catch it now. The spacecraft encounters are happening now, in late October and early November 2025. The ground-based telescopes are observing now, while the comet is still bright enough to detect. The data is being collected now, stored in computer memories, transmitted across millions of kilometers to Earth. This moment, this brief intersection of an ancient traveler with a young civilization is happening in real time, and we won't get another chance like this for years, maybe decades. Interstellar objects are rare. We've detected only 3 so far. The next one might arrive next year, or it might not arrive for a generation. We can't predict when or if another interstellar comet will pass close enough to the Sun to develop a tail that intersects with spacecraft we've already launched. This is it. This is the moment. And what we learn from it will shape our understanding of the cosmos for years to come. The history of comet observation is filled with moments of discovery that changed how we understand the universe. In 1605, Johannes Kepler observed a bright comet and used it to develop his laws of planetary motion, recognizing that celestial objects follow mathematical paths governed by gravity. In 1705, Edmund Halley predicted that a particular comet would return in 1758, proving that comets orbit the Sun and are not random atmospheric phenomena. When Halley's comet returned as predicted, though Halley himself had died by then, it was a triumph of Newtonian physics and a demonstration that the heavens follow predictable laws. In the 20th century, we began to understand what comets actually are. Fred Whipple's dirty snowball model, proposed in 1950, described comets as icy bodies that release gas and dust as they're heated by the Sun. Spacecraft missions in the 1980s and beyond, particularly the missions to Halley's Comet in 1986, confirmed this model and added incredible detail. We learned that comets contain not just water ice, but a complex mixture of frozen gases and organic compounds. We discovered that cometary nuclei are dark, irregular, and surprisingly fragile. We found that comets have been colliding with Earth since the planet formed, possibly delivering much of the water that fills our oceans and the organic molecules that served as raw materials for life. Every major comet has taught us something new. Comet Shoemaker-Levy 9, which collided with Jupiter in 1994, showed us the violence that can occur when 2 bodies meet in space and gave us invaluable data about Jupiter's atmosphere. Comet Hale-Bopp in 1997 provided some of the most detailed spectroscopic observations ever, revealing the presence of complex organic molecules. The Deep Impact mission in 2005 deliberately crashed a projectile into Comet Tempel 1, excavating material from beneath the surface and analysing it in real time. But all of those were solar system comets. Born here, orbiting here, part of our cosmic family. Their compositions reflect the conditions in our protoplanetary disk 4.6 billion years ago. They tell us about our origins, our history, the processes that led to Earth and everything on it. Interstellar objects tell a different story. The first confirmed interstellar visitor, Oumuamua, appeared in October 2017. It was already leaving the solar system when it was discovered, moving too fast for any spacecraft to intercept. Astronomers had only a few weeks to observe it before it became too faint to detect. What they saw was puzzling. An elongated object tumbling rapidly, reflecting light in unusual ways, showing no signs of cometary activity despite having passed close to the Sun. Some data suggested it might have been accelerating slightly, pushed by some force that wasn't obvious. The debate about Oumuamua continues. Was it a comet with an unusual composition? An asteroid? Something else entirely? We'll never know for certain because we couldn't study it in detail. It came and went too quickly, and we weren't prepared. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered another interstellar visitor using a telescope he built himself. This one was clearly a comet. It developed a visible coma and tail as it approached the Sun. Astronomers around the world pointed their most powerful instruments at it, and for several months we had the opportunity to study an interstellar comet in detail. What we learned from 2I Borisov was both reassuring and tantalizing. Reassuring because it behaved like our own comets. It had water, carbon monoxide, and other familiar molecules. Its nucleus appeared similar in size and composition to solar system comets. In many ways, it was ordinary. But tantalizing because the ratios of different molecules were slightly different from what we typically see. The carbon monoxide abundance was higher than expected. Some organic molecules appeared in different proportions. It was similar enough to confirm that comet formation is a universal process, but different enough to remind us that other stellar systems have their own histories, their own chemical signatures. And now we have 3 Atlas, the third confirmed interstellar object, the first interstellar comet that spacecraft will encounter in situ. This is special. This is unprecedented. We're not just observing from Earth, analysing light that has travelled millions of kilometres. We're sending instruments into the comet's environment, measuring particles directly, sampling the tail, recording magnetic field fluctuations, detecting ions that were part of the comet's nucleus just days or weeks earlier. This is the closest we've ever come to touching an interstellar object, and there's genuine suspense here because we don't know what we'll find. The models predict certain compositions, certain ion densities, certain behaviours. But models are based on assumptions, and nature doesn't always follow our expectations. What if the composition is radically different from solar system comets? What if the isotopic ratios point to formation conditions we've never considered? What if there are molecules present that we've never detected in any comet before, organic compounds synthesized in an alien protoplanetary disk perhaps? What if the magnetic field interactions are stronger or weaker than predicted, revealing something about the solar wind or the comet's internal structure that we didn't anticipate? What if the data show something unexpected? That's the question driving scientists as they wait for Hera and Europa Clipper to transmit their findings. Space exploration is full of surprises. Almost every mission has discovered something that wasn't predicted, something that forced us to revise our theories, reconsider our assumptions, expand our understanding. The Voyager missions discovered active volcanoes on Io, geysers on Triton, and revealed the incredible complexity of the outer planet's systems. The Cassini mission found liquid methane lakes on Titan and confirmed the existence of a subsurface ocean on Enceladus. The New Horizons flyby of Pluto revealed a geologically active world with nitrogen glaciers and towering mountains of water ice, completely overturning the expectation that such a distant small body would be dead and frozen. What will 3I Atlas reveal? We're about to find out. In October 2025, just weeks after the discovery of 3I Atlas was confirmed and its interstellar nature was established, a prominent scientist made headlines with a provocative suggestion. Avi Loeb, a theoretical physicist at Harvard and chair of the university's astronomy department, speculated publicly that 3 Atlas might not be entirely natural. He raised the possibility, not as a definitive claim, but as a hypothesis worth considering, that the comet could be an alien artifact, or at least could contain artificial components. Loeb has a history of such speculation. He made similar suggestions about Oumuamua in 2017, proposing that its unusual characteristics, its elongated shape, its slight non-gravitational acceleration, its tumbling motion, could be explained if it were a light sail, a thin reflective structure built by an alien civilization and sent on a journey through the galaxy. Most astronomers disagreed with that interpretation, arguing that natural explanations were more plausible. But Loeb persisted, writing a book about it and continuing to advocate for serious consideration of the artificial hypothesis. With 3I Atlas, Loeb again raised the question, what if this isn't just a comet? What if it's a probe sent by another civilization, designed to look like a comet, perhaps to avoid detection or to study stellar systems while appearing natural? What if the tail we're seeing is intentional, a way of broadcasting information or concealing the object's true nature? The mainstream scientific response has been skeptical but measured. Observations of 3I Atlas show all the hallmarks of a natural comet: sublimation of volatiles, development of a coma and tail consistent with solar heating, spectroscopic signatures of water, carbon monoxide, and dust. The nuclear size estimates, while uncertain, are consistent with known comets. The trajectory, while hyperbolic and therefore interstellar, is dynamically unremarkable, exactly what you'd expect from an object ejected from another stellar system. In short, 3I Atlas behaves like a comet because it is a comet. There's no evidence, none at all, for anything artificial about it. It's made of ice and rock, formed billions of years ago in a protoplanetary disk, ejected by gravitational interactions, wandering through interstellar space until it happened to pass through our solar system. But Loeb's speculation captures something important about the human imagination. We want there to be aliens. We want the universe to be populated with other civilizations, other intelligences, other beings who look up at their skies and wonder if they're alone. The idea that an interstellar visitor might be artificial, might be evidence of another civilization's technology, is irresistibly compelling. And there's nothing wrong with that speculation, as long as it's recognized as speculation and not confused with evidence. Science operates by proposing hypotheses and testing them against data. Loeb's artificial hypothesis is testable. If 3I Atlas were artificial, we'd expect to see anomalies in its behavior, deviations from what a natural comet would do. We'd expect strange spectroscopic signatures, unusual trajectories, perhaps even deliberate changes in course or velocity. So far, we've seen none of that. Every observation is consistent with a natural object, which means Occam's razor applies. The simplest explanation that fits the data is probably correct, and the simplest explanation is that 3I Atlas is exactly what it appears to be. A comet from another star system, no more and no less. But this dance between imagination and evidence is fundamental to how science works. We need imagination to propose new ideas, to think beyond the obvious, to consider possibilities that might seem unlikely. And we need evidence to ground those ideas in reality, to test them rigorously, to separate what's true from what we merely wish were true. Throughout history, speculation has sometimes led to genuine discoveries. Atoms were once speculative. Black holes were speculated about for decades before they were confirmed. Exoplanets, planets orbiting other stars, were long hypothesized but not definitively detected until the 1990s. In each case, speculation eventually gave way to evidence, and the universe turned out to be even more interesting than we imagined. Could there be alien civilizations out there? Almost certainly. The universe is vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars have planets. Some of those planets are in habitable zones where liquid water can exist. The chemistry of life, carbon-based organic molecules, is ubiquitous in space. It would be statistically bizarre if Earth were the only place where life arose. But that doesn't mean every unusual object we see is artificial. In fact, given how rare technological civilizations appear to be, we've detected no unambiguous signals from any other civilization in over 60 years of searching. It's far more likely that unusual objects are natural than artificial. The real surprise with 3I Atlas probably won't come from discovering it's artificial. It will come from what the object reveals about nature, because nature is endlessly creative, producing phenomena that rival anything we can imagine. Neutron stars, magnetars, quasars, gamma-ray bursts, dark matter, dark energy. The universe is full of wonders that aren't alive, aren't intelligent, but are nonetheless astonishing. And if the data from Hera and Europa Clipper reveal something unexpected in 3I Atlas's composition or behavior, it won't be because aliens built it. It will be because nature, operating under physical laws we think we understand, produced something we didn't anticipate. And that's even more exciting because it means we still have things to learn, mysteries to solve, phenomena to discover. The universe is strange enough without needing aliens to make it interesting. Though we keep looking, keep hoping, keep listening for that signal that would tell us we're not alone. Someday, perhaps, we'll find it. But for now, the wonder lies in understanding what's already here. These cosmic travelers, these frozen time capsules, these messengers from other worlds that speak to us not in words, but in chemistry, in isotopes, in the subtle whispers of ancient ice sublimating in the warmth of our sun. So what might we actually find when Hera and Europa Clipper analyse the data from their tail encounters? What measurements matter, and what could they tell us? Start with composition. The most basic question: what molecules are present in the ion tail? Hera and Europa Clipper aren't equipped with dedicated mass spectrometers optimized for cometry analysis, but their plasma instruments can still detect ions and in some cases determine their mass-to-charge ratios. This allows identification of at least the major species. We expect to find water ions, H2O+, because water ice is the most abundant volatile in comets. We also expect carbon monoxide, CO+, carbon dioxide, CO2+, and perhaps some nitrogen-bearing species like N2+ or CN+. These are the standard cometry volatiles, the molecules that have been detected in every active comet we've studied. But the relative abundances matter. In our solar system comets, water typically dominates. It's usually 70 to 80% of the volatile budget. Carbon monoxide and carbon dioxide are present but less abundant, typically a few percent each. If 3i Atlas shows a different pattern, say, much higher carbon monoxide abundance, or unusual amounts of nitrogen compounds, it would suggest formation in a protoplanetary disk with different chemistry than our own. That chemistry depends on temperature, on the abundance of different elements, on the timing of planet formation, on a host of factors that vary from stellar system to stellar system. By measuring the composition of 3i Atlas, we're essentially measuring the conditions in its birth environment billions of years ago. Then there are isotopes. Isotopes are versions of the same element with different numbers of neutrons. Carbon-12 and carbon-13 are both carbon, but carbon-13 has one extra neutron. Oxygen-16, oxygen-17, and oxygen-18 are all oxygen, but with different neutron counts. The ratios of these isotopes vary depending on where and when they formed. In our solar system, we have fairly consistent isotopic ratios because everything formed from the same molecular cloud. But in other stellar systems, especially those formed at different times in galactic history, the ratios could be different. If 3i Atlas shows unusual isotopic signatures, it would be powerful evidence of its extrasolar origin and would provide clues about the galactic chemical evolution at the time its parent star formed. Detecting isotopic ratios requires high-resolution spectroscopy, which neither Hera nor Europa Clipper can provide. But ground-based telescopes observing 3i Atlas have been attempting these measurements, and the combined data from spacecraft and telescopes could yield results. Beyond composition, there are the plasma physics measurements. When the solar wind encounters pickup ions from the comet, the interaction creates distinctive signatures. The magnetic field lines drape around the region where pickup ions are abundant, forming what's called a magnetic pileup region. This creates characteristic patterns in magnetometer data: increased field strength, rotation of the field direction, fluctuations at specific frequencies. Hera and Europa Clipper both carry magnetometers. If the ion density is high enough, they should detect these signatures. The strength and structure of the magnetic pileup tells us about the ion production rate, which in turn constrains the comet's gas production, and therefore its size and activity level. There are also energetic particle effects. When pickup ions are accelerated by the solar wind, they can reach high energies, becoming what are called energetic neutral atoms or even cosmic rays at the lower energy range. These particles can be detected by radiation monitors, providing another way to measure the extent and density of the cometary ion population. Now think bigger. What could all of this tell us beyond just characterizing one comet? It could tell us about planet formation in other stellar systems. Comets are leftover material from planet formation, the stuff that didn't get incorporated into planets. By studying comets from other systems, we're studying the raw materials and conditions that existed in those protoplanetary disks. If we find significant differences, it suggests that planet formation can proceed differently under different conditions, which has implications for exoplanet research. It could tell us about material exchange in the galaxy. We now know that stellar systems eject comets regularly. Those comets drift through interstellar space and occasionally get captured, or at least perturbed, by other stars. This means there's a kind of galactic-scale material exchange happening, a mixing process where the products of one stellar system can end up in another. If interstellar comets are common enough, they could even deliver organic molecules and water to other stellar systems, potentially spreading the building blocks of life across the galaxy. It could tell us about cosmic chemistry. The universe started with just hydrogen and helium. All heavier elements, carbon, oxygen, nitrogen, iron, everything, were created in stars and distributed by supernovae. The abundances of these elements have changed over cosmic time as more generations of stars have lived and died. By studying an object from the thick disk, formed 9 to 13 billion years ago, we're probing the chemistry of the galaxy at an earlier epoch, which helps us understand galactic chemical evolution. It could tell us something about the ubiquity of organic chemistry. Every comet we've studied contains organic molecules, complex carbon-based compounds that are the building blocks of life. If 3I Atlas also contains organics, and especially if it contains types we haven't seen before, it would reinforce the idea that organic chemistry is universal, that the ingredients for life are widespread throughout the galaxy. And here's the beautiful thing. Even if we find nothing dramatic, even if 3I Atlas turns out to be completely ordinary, similar in every way to our own comets, that would still be meaningful. It would tell us that comet formation is indeed a universal process, that the physics and chemistry that operated in our protoplanetary disk also operate elsewhere. It would be confirmation that we understand the basic processes, that our models are correct, that nature works the same way in different places and at different times. There's wonder in both outcomes, the unexpected discovery that forces us to revise our theories, and the confirmation that we've understood something correctly, that the universe follows patterns we can comprehend. This is what science is, the patient accumulation of knowledge, measurement by measurement, discovery by discovery, building an ever more complete picture of reality. Sometimes that process yields dramatic surprises. Sometimes it yields incremental understanding. Both are valuable. Both bring us closer to truth. And right now, in late October 2025, we're in the middle of gathering that knowledge. The encounters are happening. The data is being collected. Soon we'll have the results, and we'll take another small step forward in our understanding of the cosmos. Let's zoom in on the specific timeline. The dates matter because they define the window of opportunity. The brief span when two human-made machines will intersect with the ghostly trail of an interstellar visitor. For Hera, the predicted encounter window is October 25th to November 1st, 2025. That's 8 days. 8 days when the spacecraft's trajectory carries it through the region where models predict the ion tail of 3I Atlas extends. The closest approach to the tail's central axis occurs around October 28th, when Hera will be approximately 8.2 million kilometers from that axis. 8.2 million kilometers sounds far. It is far, more than 20 times the distance from Earth to the Moon. But comet ion tails are enormous structures. They're tenuous, yes, but they extend across vast distances. The tail of a bright comet can stretch for tens of millions of kilometers, creating a cone of ionized gas that sweeps through a huge volume of space as the comet moves. For Europa Clipper, the window is October 30th to November 6th. Again, about a week, overlapping with Hera's encounter but extending slightly later. Clipper's closest approach to the tail axis occurs around November 2nd, at approximately 8 million kilometers, nearly the same distance as Hera, but from a different angle and a few days later. Right now, and when I say right now, I mean at the time these events are occurring, in late October 2025, Hera is already in the encounter window. The spacecraft has been flying through space for over a year since its launch, covering millions of kilometers, executing maneuvers, checking out its instruments, transmitting data back to Earth. Its onboard computer is following the uploaded command sequences, maintaining its attitude, monitoring its systems. And sometime around October 25th, perhaps without any outward sign, Hera crossed an invisible boundary. it entered the region where ions from 3I Atlas are present. Not densely. The difference might be only a few ions per cubic centimetre compared to the background solar wind. But they're there. Water molecules that were frozen in the comet's nucleus, sublimated as the comet approached the sun, ionized by solar ultraviolet radiation, picked up by the solar wind, and carried millions of kilometers behind the nucleus. Those ions are streaming past Hera right now. The spacecraft's magnetometer is detecting subtle fluctuations in the magnetic field. Its plasma instrument is recording ion velocities and densities. Its radiation monitors are noting any changes in the energetic particle environment. All of this data is being time-stamped, compressed, stored in onboard memory for later transmission to Earth. The transmission itself takes time. Radio signals travel at the speed of light, but when you're millions of kilometers from Earth, even light takes minutes to arrive. Commands sent from ground controllers take minutes to reach the spacecraft. Data from the spacecraft takes minutes to reach Earth. There's no real-time control, no joystick piloting. Everything is automated, pre-planned, executed by algorithms and onboard computers. By the time mission controllers see the data from Hera's encounter, the encounter itself is already over. They're looking at the past, reconstructing what happened minutes or hours ago based on the telemetry streaming in. It's like watching a movie of an event that's already concluded. Europa Clipper is a few days behind. As of October 28th or 29th, Clipper is approaching the predicted tail boundary. Its instruments are primed. Its data recorders are active. The spacecraft is healthy, on trajectory, communicating normally with Earth. And then, around October 30th, Clipper also crosses that invisible line. It too begins to fly through a region where cometary ions are present. Its magnetometer responds. Its plasma instrument detects the signature of pickup ions. Its mass spectrometer, more sensitive than anything on Hera, might even be able to identify specific molecular species if the density is high enough. Two spacecraft, two sets of instruments, two independent measurements of the same phenomenon, taken from slightly different locations and slightly different times. This redundancy is valuable in science. It allows cross-checking, validation, confirmation that what you're seeing is real and not an instrumental artifact. Imagine the scene in the control rooms. At the European Space Operations Center in Darmstadt, Germany, engineers and scientists monitor Hera's telemetry as it arrives. At NASA's Jet Propulsion Laboratory in Pasadena, California, the Europa Clipper team does the same. There's anticipation, yes, but also routine. Space missions generate enormous amounts of data every day, most of it routine housekeeping telemetry. Finding the signals that matter, the subtle indications that the spacecraft is detecting something unusual, requires careful analysis, often taking days or weeks. But there's also excitement, because everyone involved knows what's happening. They know their spacecraft are flying through the tail of an interstellar comet. They know this is historic, unprecedented, a once-in-a-lifetime opportunity. Even if the signals are subtle, even if the analysis takes months, even if the results are ambiguous, they're part of something extraordinary. Now imagine the moment of crossing itself, not from the perspective of the control rooms on Earth, but from the spacecraft's perspective, if it could somehow be aware of what's happening. The scene is darkness. Perfect, absolute darkness, broken only by the distant pinprick light of the sun and the even more distant points of stars. The spacecraft is a tiny speck of metal and silicon, no larger than a car, drifting, no, not drifting, hurtling, through the void at tens of thousands of kilometers per hour. But there's no sensation of motion because there's no air, no friction, no reference frame except the slowly changing positions of distant celestial bodies. Around the spacecraft, the solar wind flows constantly, protons and electrons streaming outward from the sun, carrying with them the solar magnetic field, invisible but real, permeating all of space out to the edge of the solar system and beyond. Instruments on the spacecraft measure this wind, its density, its velocity, its temperature, its magnetic properties. Day after day, for months and years, the measurements are consistent. The solar wind is there, always, a fundamental feature of the space environment, and then, subtly, almost imperceptibly, something changes. New ions appear in the delta stream. The magnetic field begins to fluctuate in unusual ways. The density of charged particles increases slightly. The spacecraft's radiation monitors detect a shift in the energetic particle flux. The tail has arrived. Or rather, the spacecraft has arrived in the tail. It's flying through a stream of particles that originated not from the Sun but from an ancient comet, from a nucleus of ice and rock that formed around another star, that has wandered through the galaxy for billions of years, and that is now, for a brief moment in cosmic time, shedding its substance into the solar wind. The data lights flicker, metaphorically of course. There are no actual lights, as sensors record information, magnetometer readings, plasma densities, ion velocities, energetic particle counts, all of it digitized, compressed, queued for transmission to Earth. And then, a few days later, the spacecraft exits the tail region. The cometary ions become less abundant, the magnetic field fluctuations diminish, the measurements return to normal solar wind values. The encounter is over. 8 days for Hera, 7 days for Europa Clipper. That's all. In those brief windows, separated by millions of kilometers of space and a few days of time, 2 spacecraft sampled the environment of an interstellar visitor. They collected data that no human instrument has ever collected before. They touched in a very real sense something from another star system, and now we wait for the analysis. The raw data must be downloaded, processed, calibrated, analyzed. Scientists must compare the measurements to models, look for correlations, rule out instrumental effects, determine what signals are real and what are noise. This takes time, weeks, months, perhaps longer, but the data exists, the measurements were made, the moment occurred, and soon, very soon, we will know what they found. In a moment, we will know. The encounters have happened. By early November 2025, both Hera and Europa Clipper have passed through the predicted region, where 3I Atlas's ion tail extends. The spacecraft have crossed that invisible boundary. Their instruments have recorded whatever signatures were present, and now they're continuing on their primary missions, Hera toward the Didymos asteroid system, Europa Clipper on its long journey to Jupiter. But the story is far from over. In fact, in many ways, it's just beginning. Space science doesn't operate on the timescale of news cycles or social media updates. The dramatic moment of encounter, spacecraft flying through comet tail, is actually the least dramatic part from a human perspective. There's no video, no live stream, no real-time commentary, just data streaming silently from spacecraft to Earth at the speed of light, arriving minutes after it's collected, accumulating in computer systems where it will wait patiently for human analysis. The first step is data downlink. Spacecraft have limited bandwidth for transmitting data back to Earth. The radio signals are weak after travelling millions of kilometres, requiring enormous dish antennas on Earth to capture them. And there's competition for bandwidth. The spacecraft need to send housekeeping data, navigation data, primary mission data, and now this unexpected bonus data from the comet encounter. So the downlink happens gradually, over days and weeks, as time slots become available on the Deep Space Network, NASA's array of giant radio antennas scattered around the world. As the data arrives on Earth, it goes through initial processing. Raw instrument readings are converted into physical units: magnetic field strength, ion density, particle energy, whatever each instrument measures. This is where calibration comes in. Every scientific instrument has quirks, biases, known issues that must be corrected. Temperature affects readings. Aging electronics drift over time. Cosmic ray hits can create spurious signals. All of this must be accounted for before the data can be trusted. Then comes the real work: analysis. Scientists begin examining the data, looking for the signatures they expect from a comet tail encounter. Did the magnetometer readings show the predicted magnetic field draping? Did the plasma instrument detect pickup ions with the right velocities and densities? Were there anomalies in the energetic particle measurements? How do the observations compare to models? This process takes time, months typically, sometimes longer. The scientists involved aren't just working on this one dataset. They have other responsibilities, other projects, teaching duties if they're at universities, mission operations if they're on spacecraft teams. Analysis happens in fits and starts, as people find time between other commitments. And it's not just one person doing the analysis, it's teams. Groups of scientists with different expertise, different perspectives, different ideas about what the data means. They share preliminary results, debate interpretations, run simulations to see if their conclusions are consistent with physics. They write draft papers, circulate them among colleagues, revise them based on feedback. Eventually, if the results are significant, they'll submit a paper to a peer-reviewed journal. That triggers another round of waiting. The journal sends the paper to expert reviewers, other scientists in the field who read it critically, check the analysis, look for errors or alternative explanations, and ultimately recommend whether it should be published. This can take months more. The authors might need to revise the paper, address reviewers' concerns, rerun analyses with different assumptions. Only after all of this, after data, downlink, processing, calibration, analysis, writing, peer review, revision, does the information become public. A paper appears in a journal, a press release goes out, news articles are written, and the world learns what Hera and Europa Clipper found when they flew through the tail of 3i Atlas. It's a slow process, frustratingly slow if you're eagerly waiting for results, but it's necessary. Science isn't about rushing to conclusions. It's about being careful, being thorough, being honest about uncertainties. It's about getting the answer right rather than getting it first. So as of late 2025, we wait. The data exists, the measurements were made. But the analysis is ongoing, the papers are being written, and the full story won't emerge for months or perhaps years. There will be preliminary results, hints and suggestions shared at scientific conferences. There will be rumours in the astronomy community about what was or wasn't detected. But the definitive answers will take time, and that's okay. Because while we wait, we can think about what this means. Not just the specific measurements, whether the ion density was high or low, whether unusual molecules were detected, but the bigger picture. What does it mean that we were able to do this at all? What does it say about where we are as a species, as a civilization, as participants in the cosmic drama? The quiet after the action is its own kind of profound moment. The spacecraft have done their work, the data is secure, and now we reflect on what we've accomplished and what questions remain. What will we do with what we learn? How will it change us? What comes next? These are the questions that matter in the long run. Not just what we discovered about one comet, but what the act of discovery itself reveals about who we are and who we might become. Think about what just happened. An object from another star system, formed billions of years ago in a protoplanetary disk orbiting a star we can never identify, located in a region of the galaxy we can never visit, passed through our solar system, and we noticed it. Not just noticed, but studied it, analysed its trajectory, modelled its composition, predicted where its tail would extend. And then we realised that two spacecraft we had launched years earlier, for entirely different purposes, would intersect with that tail. We didn't plan this. We couldn't have. The comet wasn't discovered until 9 months after the spacecraft launched. The alignment was pure cosmic coincidence, the kind of serendipity that makes you wonder if the universe has a sense of timing. But here's what we did do. We built those spacecraft. We designed them, tested them, launched them into space on trajectories that would take them millions of kilometers from Earth. We gave them instruments capable of detecting subtle changes in magnetic fields and plasma environments. We built a communications network that can receive faint radio signals from millions of kilometers away. We trained teams of scientists and engineers who know how to operate these systems, analyze the data, extract meaning from measurements. And when the opportunity presented itself, when an interstellar comet happened to pass through our solar system at just the right time and place, we were ready. Not specifically prepared for this exact scenario, but ready in a broader sense. Ready because we've invested in space exploration, in planetary science, in the infrastructure and expertise needed to study the cosmos. This is what exploration looks like in the 21st century. Not dramatic journeys to unknown lands, not ships disappearing over the horizon, not explorers planting flags on newly discovered shores. Instead, it's machines representing us, carrying our curiosity across vast distances, sending back data that we analyze and debate and slowly, methodically, turn into knowledge. There's something beautiful about that. We sent machines to touch the wake of an object from another star. The machines have no awareness, no understanding of the significance of what they're doing, but we do. We built them with intention, with purpose, with the explicit goal of learning about the universe, and in doing so, we extended our reach beyond our planet, beyond our solar system in a sense, because even though the spacecraft never left our solar system, they sampled material from something that did. Think about our place in the universe. We live on a small rocky planet orbiting an average yellow star in the outer regions of a spiral galaxy. Our star is one of hundreds of billions in the Milky Way. Our galaxy is one of hundreds of billions in the observable universe. The scales are so vast that they defy comprehension. If you represented the Earth as a grain of sand, the Sun would be a grapefruit 2 meters away. The nearest star would be over 500 kilometers distant, and the Milky Way would span the entire width of North America. We are unimaginably small in cosmic terms. Our planet is a mote of dust. Our civilization has existed for a blink of cosmic time. Everything we've ever built, every empire that has risen and fallen, every war fought and peace achieved, every work of art created, every scientific discovery made, all of it confined to a thin film of atmosphere coating a rocky sphere that's barely visible from the nearest star. And yet we have looked up at the sky and wondered. We have built telescopes and spacecraft. We have sent our instruments across billions of kilometers. We have detected an object from another star system and managed to study it, however briefly, however incompletely. There's profound meaning in that act. It says something about curiosity, about the drive to understand, about the refusal to accept ignorance when knowledge is possible. It says something about our capacity for cooperation, the thousands of people across dozens of countries who contributed to these missions. It says something about our long-term thinking, the willingness to invest in projects that take decades to complete, that benefit future generations more than the current one. But there's also melancholy here, because the moment is fleeting. 3I Atlas is already leaving. By the time you hear these words, the comet may already be fading from view, heading back out beyond the orbit of the outer planets, returning to the darkness of interstellar space. Within months, it will be too faint for even our most powerful telescopes to detect. Within years, it will be so far away that the Sun will appear as just another star in its sky, indistinguishable from the thousands of other stars visible from its frozen surface. The encounter is over. Hera and Europa Clipper are moving on to their primary missions. The data has been collected, the moment of intersection has passed, and 3I Atlas continues its lonely journey across the galaxy, a journey that will continue for millions or billions of years, until perhaps, impossibly unlikely but not impossible, it enters another stellar system and is observed by other beings who look up at their sky and wonder about travellers from distant places. We had our moment with this visitor from another star, a brief window, a few weeks of intense observation, a handful of days when our spacecraft flew through its tail. That's all. The universe doesn't pause for us. It doesn't wait for us to finish our observations or complete our analysis. It just continues, indifferent to our presence, following the laws of physics that care nothing for human timescales or human concerns. But within that fleeting moment, we did something remarkable. We reached out. We touched, however gently, something from beyond our cosmic neighbourhood. We gathered data that will inform our understanding for years to come. We took one more small step in the endless journey of discovery that defines us as a species. And the journey doesn't end here. Because 3I Atlas is not the last interstellar visitor we'll encounter. It's not even the last one we know about. There are others coming, objects drifting through the galaxy that will eventually pass close enough to our Sun to be detected, studied, perhaps even visited by future missions designed specifically for that purpose. The age of interstellar object exploration has only just begun. On a launch pad somewhere on Earth, the exact location yet to be determined, a spacecraft is being prepared for a mission that doesn't quite exist yet. The mission is called Comet Interceptor, and it represents a fundamentally new approach to studying comets and other small bodies in our solar system. Traditional comet missions are designed years in advance. You pick a target comet, calculate its orbit, design a trajectory that will allow your spacecraft to intercept it, and then launch at exactly the right time to make the rendezvous. This works well for known comets with well-characterized orbits, but it doesn't work for interstellar objects, because we don't know they exist until they're already here, already passing through the solar system, often already leaving by the time we spot them. Comet Interceptor changes that paradigm. Instead of launching to a specific target, the spacecraft will launch and then wait. It will park itself at a gravitationally stable point in space, one of the Sun-Earth Lagrange points, and sit there, dormant, conserving fuel and power for months or years if necessary. And when a suitable target appears, whether it's a long-period comet making its first passage through the inner solar system, or better yet, an interstellar object like Oumuamua, or 2I Borisov, or 3I Atlas, the spacecraft will wake up, fire its engines, and intercept the target. The mission is being developed by the European Space Agency, with contributions from Japan's space agency, JAXA. The planned launch date is 2029, though as with all space missions, that's subject to change. The spacecraft will actually be 3 separate probes, a main spacecraft and 2 smaller subprobes, that will approach the target comet from different angles simultaneously, providing multi-point observations of the coma, nucleus and tail. This is the future, not one-off missions to known targets, but flexible, responsive missions that can react to discoveries made in real time. It's a recognition that the universe is full of surprises, that interesting things happen on timescales we can't always predict, and that we need to be ready to adapt. If Comet Interceptor had been in space during 3I Atlas's passage, it could have maneuvered for a close flyby of the nucleus itself, not just a distant tail crossing. It could have imaged the nucleus up close, revealing its shape, surface features, rotation rate. It could have flown directly through the densest part of the coma, sampling gases and dust at high concentrations. It could have provided data far more detailed than what Hera and Europa Clipper were able to collect from millions of kilometers away. Next time, and there will be a next time, we'll be better prepared. Comet Interceptor is just the beginning. There are proposals for even more ambitious missions. Spacecraft that could not just fly by an interstellar object, but actually match velocity with it, pacing alongside it for days or weeks, making extended observations. Spacecraft that could collect samples and return them to Earth. Even spacecraft that could attach to an interstellar object and ride it back out into the galaxy, becoming humanity's first true interstellar probe. These are still concepts, visions of what might be possible with future technology and future budgets. But that's how all great missions start, as ideas, as dreams, as proposals that seem ambitious or even impossible until suddenly they're not, until someone figures out how to make them work and they become reality. The story that began with 3I Atlas continues. Every observation we make, every piece of data we collect, every insight we gain informs the next mission, the next generation of instruments, the next set of questions we'll ask. Science builds on itself, discovery enabling discovery, each answer revealing new questions we didn't even know to ask. Young people listening to this today, or reading it, or watching it, whatever form this story takes, will be the scientists and engineers who design those future missions. They'll be the ones who analyze data from Comet Interceptor when it encounters its target in the 2030s or 2040s. They'll be the ones who propose the next generation of interstellar object missions, who solve the technical challenges, who make the discoveries that we today can only imagine. This is how progress works. Not in isolated bursts of genius, but in steady accumulation of knowledge passed from one generation to the next. Every mission trains a new cohort of scientists and engineers. Every discovery inspires a new wave of students to pursue careers in space science. Every moment of wonder, like 2 spacecraft flying through the tail of an interstellar comet, plants seeds that will grow into future achievements. 3I Atlas opens the door. It shows us what's possible. It demonstrates that interstellar objects aren't just abstract concepts, but real, tangible things we can study with our instruments. It proves that we're living in an era when the galaxy is not impossibly distant but increasingly accessible to our probes and our curiosity. What will we find next? What other visitors from other star systems are even now approaching our solar system, not yet detected, not yet visible in our telescopes, but coming nonetheless? What surprises await us in the chemical composition of those visitors, in the isotopic signatures that reveal their origins, in the organic molecules that might speak to the ubiquity of life's ingredients throughout the galaxy? We don't know. That's what makes it exciting. That's why we explore. Not because we know what we'll find, but precisely because we don't. The universe is full of mysteries, and each one we solve reveals 10 more. That's not frustrating. It's exhilarating. It means we'll never run out of questions. We'll never reach a point where there's nothing left to discover. The journey continues. The next interstellar visitor is out there somewhere, drifting through the dark, and when it arrives, we'll be ready. But why should you care? You, personally reading or listening to this story? Why does it matter that a comet from another star passed through our solar system? Why does it matter that 2 spacecraft flew through its tail? What does any of this have to do with your life, your concerns, your day-to-day existence? It's easy to feel disconnected from these cosmic events. The scales are so vast, the timescales so long, the distances so incomprehensible. What happens millions of kilometers away in the cold vacuum of space seems utterly removed from the concerns of daily life. Paying bills, maintaining relationships, dealing with work and family and all the immediate pressures that demand attention. And yet, you're living at a moment when we can reach beyond our star. Think about that. For all of human history, for hundreds of thousands of years, the stars were unreachable. They were points of light in the night sky, beautiful but distant, the subject of myths and legends and speculation, but never direct knowledge. The universe beyond Earth was fundamentally inaccessible. That changed within living memory. The first spacecraft left Earth orbit in the 1950s. The first humans walked on another world in 1969. The first probes left the solar system, actually crossed the boundary into interstellar space in the 21st century. And now, in 2025, spacecraft have directly sampled material from an object born around another star. This is your time. This is happening now, during your lifetime. You're contemporaries with the first generation of humans to have direct physical contact, however mediated by machines, with material from beyond our solar system. That's extraordinary. That's unprecedented in all of human history. And it's not just abstract knowledge. The science we do in space has practical applications that affect your life directly. Weather satellites predict storms and save lives. GPS satellites enable navigation and commerce. Communication satellites connect the world. Earth observation satellites monitor climate change, track deforestation, help manage resources. The technologies developed for space exploration, miniaturized electronics, advanced materials, medical imaging devices, spin off into countless civilian applications. But beyond the practical, there's something deeper. The act of exploration, the drive to understand, to discover, to push the boundaries of knowledge, is fundamentally human. It's what makes us us. Every culture on Earth has stories of explorers, of people who ventured into the unknown and returned with new knowledge. That same impulse that sent ancient Polynesians across the Pacific, that drove European explorers across oceans, that pushed pioneers across continents, that impulse hasn't disappeared. It's just changed venues. Now we explore space, and when we explore, when we discover, when we learn, we all benefit. Not just materially, though that's real, but spiritually, intellectually, emotionally. We gain perspective. We understand our place in the cosmos. We realize that we're part of something vast and ancient and ongoing, a universe that existed for billions of years before us and will continue for billions of years after. That perspective matters. It makes our problems seem smaller, not in a way that diminishes them, but in a way that makes them manageable. Yes, we face challenges: climate change, resource depletion, political conflicts, social inequities. These are real and urgent and demanding of our attention, but we're also a species that can send machines millions of kilometers to study comets from other stars. We're capable of extraordinary things when we work together, when we commit to long-term goals, when we let curiosity and wonder guide us. You are part of this story. Every tax dollar that funds space agencies, every student who pursues science or engineering, every person who looks up at the night sky and feels wonder, all of that contributes to the collective human endeavour of exploration. You don't have to be an astronaut or a scientist to be part of it. You just have to care. You just have to remain curious. You just have to refuse to accept that the universe is too big or too complex or too far away to matter, because it does matter. Every discovery changes us slightly, incrementally, but real. When we learned that Earth orbits the Sun, it changed how we see ourselves. When we learned that the Milky Way is one galaxy among billions, it changed our perspective. When we detected planets around other stars, it changed our sense of possibility. And now, as we begin to study objects from those other stellar systems, we're taking another step in that ongoing transformation of understanding. You're living through a moment of history, the first detailed study of an interstellar object's environment, the first time spacecraft have sampled material from beyond our solar system. This will be in textbooks someday, discussed by future generations the way we discuss Galileo's observations of Jupiter's moons or Hubble's discovery of the expanding universe. And you get to experience it as it happens, not as history, not as something long past, but as present reality. The data is being analysed right now. The papers are being written right now. The discoveries are unfolding in real time. So pay attention. Read the articles when they come out. Watch the documentaries. Follow the missions. Learn about the science. Ask questions. Because this is your cosmic inheritance, your connection to the universe beyond Earth. This is the story of where we came from, where we're going, and what we might become. The story continues, not just in the sky, but in you, in your curiosity, your wonder, your willingness to think about things larger than yourself. That's what makes us human. That's what drives us forward. And that's what will carry us, generation by generation, to greater understanding and deeper connection with the cosmos that is our home. The tail of 3I Atlas is a ghost now. The comet is fading, moving away, heading back out into the darkness between the stars. The ions that Hera and Europa Clipper sampled have long since dissipated, swept away by the solar wind, scattered across millions of kilometers of space until their concentration is indistinguishable from background. The spectacular sight that was visible through telescopes in October and November 2025 is dimming, becoming fainter, soon to be invisible even to the most powerful instruments on Earth. But the data remains. The measurements are secure. The knowledge has been captured. And that's what matters. Because the physical encounter was always secondary to the information it provided. The tail was just a means to an end, a way of sampling material from the comet without actually visiting it. The real prize was the data, the insight, the understanding. The tail of an interstellar comet is a reminder of the ephemeral and the eternal. Ephemeral because it exists for only a brief time, a few weeks or months while the comet is active near the Sun, then dissipating as the comet moves away and the gas production ceases. But eternal because the atoms and molecules that made up that tail continue to exist. They don't disappear, they just scatter, mixing with the solar wind, drifting through space, eventually perhaps being swept up by other comets or asteroids or planets, becoming part of other systems, other stories. Nothing in the universe is truly lost, it just changes form. The water molecules that were once frozen in 3I Atlas's nucleus, that sublimated and were ionized and carried away by the solar wind, those molecules still exist somewhere in the solar system. Maybe some of them will eventually reach Earth, swept up by our magnetosphere, raining down into our atmosphere as part of the constant influx of material from space. Maybe billions of years from now, one of those molecules will be part of an ocean on some future world, or incorporated into a living organism, or frozen again in some other comet. The circle continues, material circulating through the galaxy, from star systems to interstellar space and back again, endlessly cycling, never destroyed, just transformed. We are part of that cycle. The atoms in your body were once in other stars, other worlds, and after you're gone, those atoms will continue, becoming part of other things, other beings, other stories. This is the deep message of cosmology. We are not separate from the universe. We are the universe, a part of it that has become conscious, that can look back at itself and understand. Every atom in your body is billions of years old. Every element heavier than hydrogen was created in a star. You are literally made of stardust, and so is everything around you. The earth, the trees, the water, the air. All of it forged in stellar furnaces and scattered across space by supernova explosions. 3 Atlas is a reminder of that connection. It's a traveller from another part of the cosmic story, a piece of some other stellar system's history, that briefly intersected with ours. And in that brief intersection, we learned something. Not everything. We never learn everything. But something. Another piece of the puzzle, another data point in the infinite complexity of the cosmos. So what do we do with this knowledge? We share it. We think about it. We let it inform our understanding of the universe and our place in it. We use it to inspire the next generation of explorers and scientists. We build on it, creating new missions, new instruments, new ways of studying the cosmos. We remain curious, always asking the next question, always looking for the next discovery. And we remember that exploration is not just about finding answers. It's about the act of looking, the willingness to venture into the unknown, the courage to ask questions even when the answers might be unsettling or challenging. It's about maintaining wonder in a universe that rewards attention with beauty and insight. When those spacecraft crossed the tail, they didn't just skim dust. They brushed the history of another world. They touched something that had travelled across light years, across billions of years, carrying with it the chemical signature of an alien sun, an alien planetary system, an alien moment of cosmic history. And in touching it, however briefly, however gently, we connected with something larger than ourselves. That connection is what exploration is really about. Not conquest, not domination, but understanding. Not exploitation, but appreciation. Not taking, but learning. The ghost of Three-Eye Atlas's tail will fade into memory, but the impact of this encounter will last, in the scientific papers that will be published, in the textbooks that will be written, in the future missions that will build on what we learned, in the young minds that will be inspired to study space science, to become the next generation of explorers, to ask questions we haven't yet thought of. And you are part of that story. By caring, by paying attention, by remaining curious about the universe beyond your immediate surroundings, you participate in the grand human endeavour of exploration. You don't need to be a scientist. You don't need to work for a space agency. You just need to look up at the night sky occasionally and remember that there's more out there than we can ever fully know, and that the act of trying to know, the act of exploration, is what makes us human. The tail is gone. The comet continues its journey. But we remain, here on Earth, looking up, wondering, asking questions, building spacecraft, analysing data, learning, growing, evolving. The cosmos is vast beyond imagination, but we've touched it, and it has touched us back. That's the story of Three-Eye Atlas, a visitor from another star, a tale of ions and dust, two spacecraft in the right place at the right time, and a species that looked up at the sky and wondered, and then built machines to find out. The universe is not empty. It's full of stories, and this is one of them. Your story continues, the cosmos awaits.